Krypton is a chemical element with symbol Kr and atomic number 36. It is a member of group 18 elements. A colorless, odorless, tasteless noble gas, krypton occurs in trace amounts in the atmosphere, is isolated by fractionally distilling liquefied air, and is often used with other rare gases in fluorescent lamps. Krypton is inert for most practical purposes. Krypton, like the other noble gases, can be used in lighting and photography. Krypton light has a large number of spectral lines, and krypton's high light output in plasmas allows it to play an important role in many high-powered gas lasers, which pick out one of the many spectral lines to amplify. There is also a specific krypton fluoride laser. The high power and relative ease of operation of krypton discharge tubes cause the official length of a meter to be defined in terms of the wavelength of the 605 nanometers spectral line of krypton-86. History. Krypton was discovered in Britain in 1898 by Sir William Ramsay, a Scottish chemist, and Maurice Travers, an English chemist, in residue left from evaporating nearly all components of liquid air. Neon was discovered by a similar procedure by the same workers just a few weeks later. William Ramsay was awarded the 1904 Nobel Prize in Chemistry for discovery of a series of noble gases, including krypton. In 1960, the International Conference on Weights and Measures defined the meter as 1,650,763.73 wavelengths of light emitted by the krypton-86 isotope. This agreement replaced the 1889 International Prototype Meter located in Paris, which was a metal bar made of a platinum-iridium alloy. This also obsoleted the 1927 definition of the angstrom based on the red-cadmium spectral line, replacing it with 1A equals 10-10 meters. The krypton-86 definition lasted until the October 1983 conference, which redefined the meter as the distance that light travels in a vacuum during 1,299,792,458 s. Characteristics. Krypton is characterized by several sharp emission lines, the strongest being green and yellow. It is one of the products of uranium fission. Solid krypton is white and has a face-centered cubic crystal structure, which is a common property of all noble gases. Isotopes. Naturally occurring krypton is made of 6 stable isotopes. In addition, about 30 unstable isotopes and isomers are known. 81 Kr, the product of atmospheric reactions, is produced with the other naturally occurring isotopes of krypton. Being radioactive, it has a half-life of 230,000 years. Krypton is highly volatile when it is near surface waters, but 81 Kr has been used for dating old groundwater. 85 Kr is an inert radioactive noble gas with a half-life of 10.76 years. It is produced by the fission of uranium and plutonium, such as in nuclear bomb testing and nuclear reactors. 85 Kr is released during the reprocessing of fuel rods from nuclear reactors. Concentrations at the North Pole are 30% higher than at the South Pole due to convective mixing. Chemistry. Like the other noble gases, krypton is highly chemically unreactive. In fact, before the 1960s, no noble gas compounds had been discovered. However, following the first successful synthesis of xenon compounds in 1962, synthesis of krypton difluoride was reported in 1963. In the same year, KrF4 was reported by Gross al., but was subsequently shown to be a mistaken identification. Under extreme conditions, krypton reacts with fluorine to form KrF2 according to the following equation. Kr plus F2. KrF2 compounds with krypton bonded to atoms other than fluorine have also been discovered. There are also unverified reports of a barium salt of a krypton oxoacid. Kr plus and Krh plus polyatomic ions have been investigated, and there is evidence for KrXe or KrXe plus. The reaction of KrF2 with B3 produces an unstable compound, Kr2, that contains a krypton-oxygen bond. A krypton-nitrogen bond is found in the cation HCnKrF+, produced by the reaction of KrF2 with HCnH plus ASF-6 below -50 degrees Celsius. HKRCN and HKRCCH were reported to be stable up to 40 K. Krypton hydride 4 crystals can be grown at pressures above 5 gigapascals. They have a face-centered cubic structure where krypton octahedra surrounded by randomly oriented hydrogen molecules. Natural occurrence. The Earth has retained all of the noble gases that were present at its formation except for helium. Krypton's concentration in the atmosphere is about 1 ppm. It can be extracted from liquid air by fractional distillation. The amount of krypton in space is uncertain, as the amount is derived from the meteoric activity and that from solar winds. The first measurements suggest an overabundance of krypton in space. Applications. Krypton's multiple emission lines make ionized krypton gas discharges appear whitish, which in turn makes krypton-based bulbs useful in photography as a brilliant white light source. Krypton is thus used in some types of photographic flashes used in high-speed photography. Krypton gas is also combined with other gases to make luminous signs that glow with a bright, greenish-yellow light. Krypton mixes with argon as the fill gas of energy-saving fluorescent lamps. This reduces their power consumption. Unfortunately, this also reduces their light output and raises their cost. Krypton costs about 100 times as much as argon. Krypton is also used to fill incandescent lamps to reduce filament evaporation and allow higher operating temperatures to be used for the filament. A brighter light results which contains more blue than conventional lamps. Krypton's white discharge is often used to good effect in colored gas discharge tubes, which are then simply painted or stained in other ways to allow the desired color. Krypton is also capable of much higher light power density than neon in the red spectral line region, and for this reason, red lasers for high-power laser light shows are often krypton lasers with mirrors which select out the red spectral line for laser amplification and emission, rather than the more familiar helium-neon variety, which could never practically achieve the multi-watt red laser light outputs needed for this application. Krypton has an important role in production and usage of the krypton fluoride laser. The laser has been important in the nuclear fusion energy research community in confinement experiments. The laser has high beam uniformity, short wavelength, and the ability to modify the spot size to track an imploding pellet. In experimental particle physics, liquid krypton is used to construct quasi-homogeneous electromagnetic calorimeters. A notable example is the calorimeter of the Na-48 experiment at CERN containing about 27 tons of liquid krypton. This usage is rare, since the cheaper liquid argon is typically used. The other parameters relevant for calorimetry application are radiation length of X0 equals 4.7 centimeters, density of 2.4 grams per cc. The sealed spark gap assemblies contained in ignition exciters used in some older jet engines contain a very small amount of krypton-85 to obtain consistent ionization levels and uniform operation. Krypton-83 has application in magnetic resonance imaging for imaging airways. In particular, it may be used to distinguish between hydrophobic and hydrophilic surfaces containing an airway. Although xenon has potential for use in computed tomography to assess regional ventilation, its anesthetic properties limit its fraction in the breathing gas to 35%. The use of a breathing mixture containing 30% xenon and 30% krypton is comparable in effectiveness for CT to a 40% xenon fraction, while avoiding the unwanted effects of a high-fraction xenon gas. Methods for the detection of concentrations of krypton-85 in the atmosphere have been used to detect suspected clandestine nuclear fuel reprocessing facilities in North Korea and Pakistan. These facilities were detected in the early 2000s and were believed to be producing weapons-grade plutonium. Precautions. Krypton is considered to be a non-toxic asphyxiant. Krypton has a narcotic potency 7 times greater than air, so breathing a gas containing 50% krypton and 50% air would cause narcosis similar to breathing air at 4 times atmospheric pressure. This would be comparable to scuba diving at a depth of 30 meters and potentially could affect anyone breathing it. Nevertheless, that mixture would contain only 10% oxygen and hypoxia would be a greater concern.